right, welcome to this quick discussion on complex variables. And I had a question based upon a recent presentation that I did, asking some really good questions on why I was doing what I was doing with regard to trying to add impedances and subtracting impedances and whatnot. And what I'll say is that complex variables is something the power systems engineer is taught in school on a technique or a methodology, a mathematical method to add what we call complex variables. And what do we mean by complex variables is that if you take a look at like resistors, or if you take a look at conductors, transformers, a busway, motors, various components within an electrical power distribution system, we represent those in a circuit as an impedance. But it's not just a resistor. They're not just a reactor. They are a combination of a resistor and a reactance in series. So if you look at a conductor like Table 9 in Chapter 9 of the National Electrical Code, where we have the impedance values of conductors, you'll see a column for your R, your resistance, and you'll see a column in there for X, your reactance. And then if you look at the notes, it'll show you that there's a Z component, it's an impedance value. Now, I'll tell you basically what's going on. What complex variables does for us is it tells us, look, you can take that resistance and reactance and go back to trigonometry, and we can represent a conductor impedance as an R and an X, as a triangle where a hypotenuse is X and the horizontal, the X-axis, is R, and the hypotenuse is your equivalent Z. This is a right triangle, and that is theta. And we are basically in the world of trigonometry. So what complex variables tells us is, look, represent each of these components as a triangle and use the rules of trigonometry to determine values, angles. And I can represent a conductor impedance. I can represent any electrical components of impedance from a complex variable. Remember, we're not talking, what we would typically represent this as is a resistor and an inductor, R and an X. So if you did, remember, circuit diagrams, if I was doing a problem, and I wanted to calculate I, and this is R, or let's say there's two resistors. This is R1 and that is R2. I would take I is equal to V over the sum of R1 plus R2. But what if R1 and R2 weren't just R1 and R2? What if R1 is Z1 and R2 is Z2, and these are represented by a resistor and a reactance in series with each other? Now, how do I add those together? How do I divide those numbers? Because remember, if I had this going on, that portion of the circuit, I can't just add these two resistances together. I have to take R1, I take R1 times R2 divided by R1 plus R2. That's how I would combine those two resistances. But now, complicate that even more by saying R1 is not just R1, R1 is R plus JX. It's more complicated. Complex variables helps me do this combination of series and parallel reactances. So I can take any conductor and represent them in this format. So let's say, for example, that I have an R of let's say my resistance is 3 and my reactance is 100. based upon the rules of trigonometry, I know that z is equal to r squared plus x squared. So z in this case is equal to the square root of 3 squared plus 100 squared. And I'm going to do that on my calculator. So that would be 9 plus 100 squared. Square root is 100.045. So z is 100.045. That's because if you drew this to scale, you'd have a very small 3 and a very tall x, right? That angle theta is going to be pretty big. Now, how do I calculate theta? So how do I calculate theta? If we go back to what? The rules of trigonometry. Go to delete. We know that tangent of theta is equal to opposite over adjacent, x over r. And we also know that the inverse tangent of x over r is equal to theta. An inverse tangent is a function on your calculator. So if I do inverse tangent of 100 divided by 3, I get 100, 3 divide, inverse tangent, 88.28. So this angle is 88.28 degrees. It's almost all right. That's almost 90 degrees because x is really big and r is really small. So that gives me, if this was my conductor, knowing the resistance and the reactance, I know what I call and what complex variables calls rectangular coordinates. Now, rectangular coordinates is when we would represent z as an r plus a jx. And that j is what we call an operator. It's a number. It's an imaginary number. It's used to represent the impedance, the x portion. But when I get into the math and I'm doing complex variable math, I'm going to treat j as a number, and we'll talk about that more when we get into multiplication. So I can say z is equal to 3 plus j 100. So I know a lot about this little equation here, this triangle and this conductor. I know its angle, I know its r resistance, I know its x, I know its impedance z, and I can put it into rectangular format. I can put it in polar format as well. Polar format is represented as the magnitude of z is equal to the magnitude of z at an angle theta. What's my angle theta? 88.28. How did I find that? Inverse tangent of x over r. So, and what's my magnitude of z? 100.045. So I can represent this triangle as 100.045 at an angle of 88.28 degrees. So those are two ways that I have to represent this triangle or this conductor. Rectangular and polar. We call these phasors. All right? So, and it's important to understand both of these because when we start to add and subtract and multiply and divide complex numbers, meaning adding impedances or either in series or in parallel with each other, I'm going to need both of these because one will be easier than the other to do the operation. So let's take another conductor. So we have, this is C1. Now let's just do C2. I have everything I need for this. Do delete, erase that, and erase that. Now we're going to do a C2. And C2 is going to have an R and an X of 8 and 17. It's a right angle. We have to calculate theta, and we have to calculate the hypotenuse. What's the hypotenuse? 17 squared plus 8 squared, square root of that. So 17 squared, 8 squared, add those two together, take the square root, and that is 18.788. 18.788. What's my angle? Is inverse tangent of 17 over 8. 17, 8 divide, inverse tangent, 64.7989. So we're going to call that 64.8. Now I have two conductors here. I have one that is a 3 plus J100. I have another which is an 8 plus J17. I have one which is a 100.045 at an angle of 88.28 degrees, and another which is 18.788 at an angle of 64.8 degrees. Now, I just can't add 100.45 and 18.788 to get my total impedance. You could. If you did, you would have a higher impedance value, which would result in a lower fault current value if you're doing a fault current study. If I'm doing a voltage drop study, I would have a higher impedance value, which would result in a larger voltage drop than what I actually have. So depending upon the calculation you're doing, using that hypotenuse in your equation can make life a lot easier because you don't have to worry about the complex variables, but you have to understand what your end goal is and whether or not you're conservative in the right direction. Again, if I'm doing a short circuit study and I'm worried about interrupting radiums, so I want the highest fault current that I think I could have because I don't want to pick an overcurrent device that has a lower interrupting rating, then I would not want to take 18.788 and add it to 100.045 and do my equation because that would be a larger impedance than what I actually have. And we're going to do the math for you. We're going to show you the comparisons. All right, so what we're going to do now is we're going to take and we're going to create a circuit, and we're going to put both of these in series, C1 and C2. Now, what do we say? C1 is 3 plus J100. C1 is equal to 3 plus J100. C2 is equal to 8 plus J17. 8 plus J17. Now, whenever I have conductors in series like this, I just add the R's and add the X's. So I would do this. This is 11, and this is 117. So my C total is 11 plus J, 117. Now, what is that equal to in polar coordinates? 11 squared plus 117 squared, square root, 117.516. 516. At an angle of 117 divided by 11, inverse tangent, 84.63 degrees. Now, the hypotenuses were 100.45, 0.045, and 18.788. 18.788 plus. That comes out to 118.83. By doing it via complex variables, I know that my magnitude is actually 117.516. The difference is 1.317. Now you might say, boy, that's not very much. And for these two, it's not very much. But if you're looking at a very large power distribution system and you're adding a lot of conductors in your series and paralleling conductors, those numbers make a difference. They add up quickly. So especially if I'm using per unit, and then I'm using very small numbers, small changes in decimals makes a big difference. So, but what I'm showing you is that adding these two together, and basically what we did was we took two triangles like this. We took a 3 plus 100, and then this one was 8 and 17. And we created one larger triangle. 3 and 8, 117. That was 117, and that was 11. So we know that our new triangle looks like this. And we know our new angle, 84 degrees. And this is 117.516. And this is 117, and that's 11. So that's adding triangles, and we do that, adding the r's, adding the x's, and following our rules for square root of r squared plus x squared. Okay, now that's adding. Now what if I have to multiply? And when would I have to multiply? I would have to multiply if I'm doing something like this, right? I have C1 and C2 in parallel with each other. Now I have to take C1 times C2 divided by C1 plus C2. We just did the C1 plus C2 up here. That's 117.516. So that is 117.516 at an angle of 84.63. But how do we multiply C1 and C2? So I'll tell you a trick. Complex variables tells us that C1 times C2, Z total, is equal to magnitudes of C1 times the magnitude of C2 at an angle of theta 1 plus theta 2. So if I use polar coordinates instead of the rectangular, if I go back to this and I use 100.045 at an angle of 88.28 and 18.788 at an angle of 64.8, I can multiply 100.045 times 18.788 and then add the angles. So let's do that. C1 times C2. Let's do C1 times C2. So let's do it up here. All right, so 100.045. 100.045. I'm going to do this. I'm going to grab this. Copy. Paste. See if I can move it down. Okay, so I know redo. So I know C1 is equal to 100.045. C2 is equal to 18.788. I got to get the angles. Okay, let's get the angles. 88.28, 64.8. 88.28, 64.8. Those are my angles. So if I want to multiply C1 times C2, I take 100.045 times 18.788 at an angle of 88.28 plus 64.8. So 100.045 times 18.788 is 1,879.6455 at an angle of 88.28 plus 64.8, 153.08 degrees. Well, what's 153.08? I have my axis is there. This is 90 degrees. So 153.8 is somewhere over here, right? So that's what that is. And in reality, my x now is negative. That is 0, and these are negative, and that's positive. That's positive, that's negative. It tells me my x value would be negative. All right, so and we're gonna learn that when we do the manual. Now, if I was going to manually multiply, so there's my C1 times C2, and I would have to divide that by my C1 plus C2 to do the parallel. But before we do that, let's manually multiply C1 and C2. Let's do this. I'm going to copy this. Copy. Come down to a nice clean sheet. Paste. I'm going to move this up a little bit. All right, so we know we have 3 plus J100. And we want to multiply that by 8 plus J17. Okay, now I don't need this anymore. Delete. And let's move this up. I'm going to multiply these two numbers together. To do that, I take 3 times 8 plus 3 times J17, and then 100 times 8 plus 100 times J17, or J100. Now, what I will tell you is, before we get into that, the operator J, we know J squared is equal to a negative 1. That's going to be an important parameter to remember. So when I multiply J100 times J17, I'm doing J squared and then 100 times 17. And J squared is a negative 1. Let's do the math. 3 times 8 plus 3 times J17 plus J100 times 8 plus J100 times J17. 24. Just going to do the math. 17, 3 times 51. There's a J, 51. And this is J, 800 plus J, oh, nope. That would be a negative. So this would be minus, right? Because J squared is a minus 1, so it's a minus. So this would be minus 1,700. Okay, that's a minus 1,700. So 24 minus 1,700. 24, 1,700 minus is a negative 1,676. 1,676. And plus J, 5,851. Now let's do the squared. 1,676 squared. 851 squared plus square root is 1,879.7 at an angle of 851 divided by a negative 1676. 1676 negative, divide. Inverse tangent is a minus 26.919. Minus 26.919. So a minus 26.919, I look at this, that's this portion of that angle. Minus 26.919. To get this, I have to subtract, or I have to, take 180 plus 20, or minus 26.919. So if I take 180 and add that, it's 153.1, 153 degrees, 153. So I could say this is 1879.7 at an angle of negative 26.919, or 1879.7 at an angle of 153.08 degrees. Now, what was our other answer? 1879.6455 at an angle of 153.08. There's your 150, 1879.7, 1879.64, 0.7, 0.06 off, 0.05 off. So my numbers came out the same, but this is the long way to do it. Polar coordinates, using polar coordinates lets me simply multiply the magnitudes, add the angles. So let's do this. Insert, duplicate, new slide, duplicate. So we know C1 and C times C2, we know C1 times C2 is 1,879.6455 at an angle of 153.08. Let's get rid of all of this. Delete. And let's copy this. Remove it. Now we're going to divide. And by keeping it in polar format, to divide complex numbers, you divide the magnitudes and then you subtract the angles. So this would be 1,879.6455 divided by 117.516 at an angle of 153.08 minus 84.63. Let's do the math. 1879.6455, 117.516 divide, and that is 15.99, so we'll call this 16 at an angle of 153.08 minus 84.63 is 68.45 degrees. So the Z equivalent of those two in parallel is 16 at an angle of 68.45. Complex variables helps me get there. Now let's just look at, what if we just use the magnitudes of C1 and C2? What were those? C1 was 100. So if I just did this without doing the complex math, I had, let's do an insert, duplicate. And let's delete all of this stuff. Let's delete all of this. I don't want to do that. Delete all of this. Delete. And let's say that I was just going to forget about the complex variables. I was going to take 100.045 times 18.788 and divide that by 100.045 plus 18.788. What would I get? Let's do the math. 100.045, 18.788 times. We'll do that again. 100.045, 18.78 times. And then I'm going to divide that by 100.045 plus 18.788 plus divide 15.82. So 15.82, if I ignore all the complex math, 16 if I don't. Now, you say, boy, Tom, that was a lot of math and a lot of stuff for a difference of 0.18, okay? And yes, but in this case, we're only dealing with C1 and C2. When you're doing a power systems analysis study and you're adding all of the complex variables, and I just pulled some numbers out of my butt, but in any case, when you're dealing with impedances that are really small and you're down to those decimal points, way far to the right of the decimal point, every little bit counts. So, and we want to be as accurate as we can. So we use complex variables to add impedances, subtract impedances, divide impedances to get our numbers. If we are doing a voltage drop study, can we just use Z? Yeah, you'll have more voltage drop than what you actually have. And again, it'll depend upon all your different reactances and all your different impedances. I just had these two conductors. If I had a very high inductive and very low resistance, and I added more conductors in series or parallel, then the errors add up considerably, especially when you get into a large power distribution system. So there are shortcuts you can take, but you have to understand the conservative nature. You have to understand that the hypotenuse is the longer of the two. Breaking things down, you'll have a smaller impedance number if you break it down to real and reactive using complex variables than if you just used Z. And that might be fine for voltage drop, but it might not be fine for short circuit studies. It might not be fine for arc flash analyses. So you just got to think about your methods and any of the assumptions that you want to make. If you just want to use X, you can just use X as well and forget about R and Z. That's sort of like a compromise between the two. But if you have something that is a very small X and a very large R, using X would not be a good idea. So this is just an insight to the topic of the whole topic of complex variables. So what I showed you, as a summary, when you add complex variables, you keep them into rectangular format. And you add the R's, and you add the X's separately, and you're golden. When you multiply, you're going to want to use polar format, and you take Z1 times Z2 at an angle of theta 1 plus theta 2. When you divide, you use polar coordinates, and you take Z1 divided by Z2 at an angle of theta 1 minus theta 2. Hopefully that helps you understand what complex variables is all about. You don't have to worry about the J operator and the square of that and any of the other functions that it has. If you just stick to use rectangular for addition and use polar for multiplication and divide. Everything else will just fall out. All right. That's just my quick overview, a sort of quick overview of complex variables. Hopefully, you got something out of that session. And, if you did, then please subscribe to my channel. Hit the thumbs up. Come on back. Keep watching. Give me some feedback. Tell me what you want to hear about. Take a look at the other study that I just did on short circuit current calculations. I'll put it up there in the corner. I just did, it's a 2.5 hour session of a manual calculation for a small power distribution system using the per unit method and complex variables, just like what I covered today. This will help you understand maybe some of the math that I did in that analysis. So please, thank you for what you do for electrical safety. Thank you for what you do for the electrical industry and your engagement. God bless, stay safe, and please stay healthy. Until next time.